Hi everybody, I am Emilio Lauret from Universidad Nacional del Sur in Bahía Blanca, which is the beginning of Patagonia, Argentina. This is a pre-recorded talk for the third Geometric Analysis Festival. I wish to thank its organizer, Hojo Lee, for this fantastic idea and to allow me to share my results here. Okay. Let's start with two slides of preliminaries, very general. Fix a closed connected Riemannian manifold. Closed means compact and without boundary. Associated to this object, we have a distinguished differential operator, which is called Laplace-Beltrán operator. We will not need to this talk the explicit expression for this operator, which acts on functions. Okay, we will not need. We will need the following because of some properties of these operators. The spectrum, which means the collection, the multiset of eigenvalues, is real, actually non-negative, and is discrete, which means that there are no accumulation points on the real line. Okay, in other words, if you put in order, they go to infinity. Okay, the numbers go to infinity. And here there is one distinguished element, which is this one, right? Because 0 is always an eigenvalue with multiplicity 1, because the constant functions, and this is connected. So it's, in general, is the eigenvalue 0 has multiplicity the number of connected components. But here it has multiplicity 1. So there is this element, which is the smallest positive eigenvalue, is called the first eigenvalue, or also the fundamental term. And what I need that you believe at this point, if you have no experience with this operator, is that this number is very important. It's very important to have information, estimate or something is very important. And Xintong Yao explained this. He wrote that while this constant has analytic importance, it also gives a strong insight in the geometry of the manifold. Okay, it has some estimates. Estimate for lambda 1 has application in problems in analysis and geometry and more places. Okay, and this is the second slide of preliminaries. Let's recall what is a homogeneous Riemannian manifold. And this is when the isometry group acts transitively on it. Roughly speaking, is that there is no any distinguishing point. Every point looks in the same way, right? Because having an isometry from any 2 points is, in particular, if you wish to compute some kind of curvature, just do it in 1 point. It's the same. Okay, it's enough. And in particular, the scalar curvature is constant. It's a function. It's a constant function. Okay. And it is well known that such object, compact object, can be written in this way, can be realized in this way, where G is a compact Lie group acting transitively on M by isometries, maybe smaller than the isometry group, okay? Maybe smaller, which is useful sometimes. And well, if you take the isotropy separable, you have this diffeomorphism. And moreover, the Riemannian metric of M is identified with the G invariant metric on G over K. Okay? And actually, if you fix G and K, the space of G invariant metrics is parameterized in Lie theoretical terms in a pretty simple way. Okay? But it is not understood, this space, up to isometries. That's a problem. Okay? But it is clear. It is well understood as whole set of G invariant metrics. And here we will introduce some very important particular case for this talk, and it's when K is trivial. Okay, pick G, a compact connected Lie group. We assume connected here. G connected. And well, the space of G invariant matrix coincides with the space of left invariant matrix. Left invariant matrix. And each of these metrics is parameterized, has associated an inner product on the Lie algebra, G of G. What means that? Well, you have a point E and a point G, right? And of course, you have the tangent space here and the identity, which is identified, naturally identified with the Lie algebra. And here you have a very well known diffeomorphism, which sends X to G times X. Okay, so this diffeomorphism sends the trivial element to G, and so identifies the differential of these diffeomorphisms identifies the identity, the tangent space at the identity with the tangent space at G. So if you translate an inner product here to any other tangent space using this, you will obtain, it turns out that this is the Riemannian metric. And this Riemannian metric is actually these elements are isometries, okay, with respect to this Riemannian matrix. And because this, of course, is transitive, it becomes a homogeneous manifold. Okay? This will be very important for this talk, this case. So we are close to state the problem, but first let's remember some result from 1980 by Peter Lie. He proved that for every compact connected homogeneous Riemannian manifold, one has this inequality. Okay, and now that the dimension of M is arbitrary. It's arbitrary. Okay, and of course this constant does not depend on G, on M, on nothing. Okay, pi squared over 4. And it is easy to see that the upper bound does not hold the analogous, okay, the reverse inequality here, right? Because this time this is not bounded by above. Why is that? Well, pick the round metric of the sphere, the one that has, for instance, constant sectional curvature 1, and it is well known that this number is equal to d, and this is equal to d, and this is equal to pi. The diameter is realized as the distance between the poles. Okay, and this goes to infinity when d does it. Okay, this goes to infinity. So the reverse inequality doesn't exist, doesn't hold. But I guess you also ask yourself about what about if you fix the dimension of M? Because of course here we are changing the dimension. What about if you fix the dimension of M? Well, this is an open problem, and a few years ago, Eldredge, Gordin, and Solovkoste made a precise conjecture for a particular case of this. And the particular case is the one that we mentioned in the previous slide. Okay, pick any compact connected Lie group, and they claim that there exists a positive constant depending only on the Lie group, such that these terms, this time this, is bounded by above by this constant uniformly for every left invariant metric G on G. Okay, this is the conjecture. This for a restricted class of homogeneous manifold. Those with compact Lie groups and those with left invariant matrix. Right? Well, the same author in this article from 2018, proposed a very detailed strategy to prove that conjecture, because they prove that these holes, provided G is uniformly volume doubling. Okay, what means that? This means this. In general, volume doubling means this, okay? Now that this is the volume of the ball of centered at X of radius 2r and here r, right? And the important thing is whether this is bounded by above. Now that we are in an homogeneous case, right? So it doesn't matter of X, this number, so this is not important. And something else is that this is important for R very small, because for R sufficiently large, these balls cover the whole space G because it's compact, so this is constant. So this is important for R small. And the word uniformly is here because this term, this should be for a particular metric. This is of course known to be for a fixed G. This is of course finite, but the point is you take the supremum over every left invariant metric on G. Okay, that's the point. And they prove if this condition holds for G, then the conjecture holds. Okay. And well, it seems that it is obvious that any torus, any compact abelian connected group, is uniformly doubling because it's locally, geometrically speaking, locally in Euclidean space. And they prove in the same paper, the author, that SU2 is uniformly doubling. Okay, and it's almost the same proof hold for SO3. Okay, and these are of course compactly groups of dimension 3, are the simplest non-commutative compactly groups, right? And this tori SU2 and SO3 are the only cases known so far. Okay, the only particular cases where the conjecture holds. Remember, the conjecture holds for every compactly group G, but these are the only cases known so far. And I was able to show in a paper published in 2019, I was able to obtain an explicit expression for these numbers in terms of some of the metric eigenvalues that I will explain later, some numbers related, associated to the metric. And well, I was also able to, explicit expression for this, and I was able to bound the diameter in terms of these eigenvalues, okay? And this independently estimates of both factors. When we put together, we obtain this, okay? We obtain this. So this is an alternative proof for this result, okay, which was already proved, right? And this is also an alternative proof in this particular case to Peter's Lee's theorem, okay, with constant a little better than those pi square over 4 he proved, but of course it result holds for every compactly group, right? So we could improve a little bit, right? And well, let me try to explain what is going to be the approach and the precise problem in this talk. So pick G, any compact connected group of dimension M. This is going to be the dimension from now on. Denote by Gothic G the Lie algebra, and fix a bi-invariant metric on G. Okay. Remember, compactly group, and though with the bi-invariant metric, is a symmetric space. Right. So we already mentioned it that the space of left invariant metrics are in correspondence with inner products G. And let me denote the corresponding inner product, the one corresponding to the fixed bi-invariant metric, by as this, right? And of course, the inner products are also parameterized by positive definite symmetric endomorphisms of G, right? With respect to this fixed inner product, right? How is that? Well, you pick any metric, any inner product, well, any metric associated, it has associated some inner product, and this inner product can be written in this way, with this element, some element here, right? A positive definite symmetric endomorphism. And in the other, this is going to be the notation, phi sub G. And in the other way, if you fix some element here, it induces some inner product and some metric that are going to be denoted with this sub-index, right? And note, this is going to be important, that the identity map, which of course lies here, returns the bi-invariant metric, right? Because if you put the identity, this is the bi-invariant metric, this inner product, and it's in correspondence with the bi-invariant metric, right? Okay, let us denote by these numbers the eigenvalues of this. Of course, this is positive definite symmetric map, so the eigenvalues are positive, real positive. And well, let me denote with this square that it is going to facilitate some things. Okay, they are positive. And here is a more precise goal. We want to estimate in terms of these numbers, mu k, remember mu k squared are the eigenvalues. We want to estimate these terms, these objects, the first eigenvalue and the diameter independently in terms of these values. Okay? And the conclusion, this is an extension of the strategy using in the alternative proof for the conjecture for SU2 and SO3. And we will obtain that these independent estimates are not going to be sufficient to bound this time the square of this. Okay? But we will give some partial answer to the conjecture. Okay? So let me proceed. Some useful facts before to give a more detailed goal. This is quite well known for every positive real number. We are, by the way, let me abbreviate. G, the capital G, the group is going to be fixed, right? So just let me denote the diameter of G to abbreviate these and also this, okay? So for every positive scalar, we have these. These are pretty well known, and this is not difficult at all. And they imply this, right? That this time the square of this, now that these numbers are going to cancel, the square of this is going to cancel with this. So this is invariant by homothesis, and the same with the rest, right? And actually, know that this is the term, the functional that we want to bound by above, right? This is invariant by homothesis, okay? And let me prove a lemma, a very simple lemma. Take two, remember the left invariant metrics are in correspondence with positive definite symmetric endomorphisms of the Lie algebra G, right? And take two of them related in this way. This means that this minus this, they are positive definite, but this inequality means this minus this is positive semi-definite, right? Has eigenvalues greater than or equal to 0. So we will see that this inequality implies this inequality and the reverse inequality here, okay? And well, what is the definition of this? It's just this. This minus this is semi-positive, semi-definite. And now that this is exactly the definition of this inner product, the inner product associated to this, right? The inner product associated with this. And what we obtain with this condition is that the metric are less than, there is an inequality between the metrics. And by a monotonicity argument, we obtain that the diameter satisfies to the, it's not immediately, but this is not immediately, but it can be done, okay? And here we have the reverse inequality, okay? So now let's see some simple, we will call simple estimates. So fix a left-invariant metric, which is the same as fix an element here. Let me denote mu k the eigenvalues of, remember, mu k squared are the eigenvalues of this, right? And well, because we have m different eigenvalues, you may take m different eigenspaces or eigenvector, and these are the multiples of these eigenvectors, right? This element diagonalized, so we are taking some basis of eigenvectors, and we write in this way, right? Phi is in this one-dimensional space is the identity, right? It's multiple. This is the eigenvalue, right? And remember that they are ordered, right? So this mu I square is less than or equal to mu m square, and the same in the reverse direction, right? Mu I square is greater than or equal to mu 1 square, right? And then, since these numbers does not depend on A, we put just outside, and this is the identity one, right? This was very simple. That's why we have this word here, simple. And well, the previous lemma, remember, this is the statement, the summary of the statement of the previous lemma, gives that the diameter associated to the left-invariant metric associated with phi is less than or equal to the diameter of the left-invariant metric associated with this and the positive definite symmetric linear map. Okay, and the same with the rest of the. Remember, here we put m in the other side because it's reversed the inequality, right? But now that we can take out this element, this is pretty simple here, right? This is an easy exercise. And now, because the useful facts from the previous slides, we can take out this. Sorry. First, replace this path by G0. We mentioned this, yes? Right? The metric associated to the identity map is the fixed bivariant metric. And now we put this, we take out these factors outside of this function, right? And well, I just copy and paste this here, and I wish you focus in this index m1 m, okay? And the idea, now we are in position to give a precise goal of what we want, and it's the following. Well, here we have an index m, which means that this element times 1 over this is bounded by above. But what about, can we put some index? Remember, m is a dimension of m, so m is the largest index possible. So can we put here an index k is smaller than m? Actually, what we want is to bound this over this with mu k, with k as small as possible, right? Because m is the largest, and the same with the rest, right? Here we can put mu k We can bound by above by a positive number, of course, because this is always bounded by 0. But we can bound diameter over mu k with k as large as possible. And the same with the lambda 1, right? This is the precise goal. And of course, this should hold for every left-invariant measure, right? This number will change, of course, because this holds for this very particular index 1 and m. But there might be some positive number that is bounded this over mu k, right? So here is the first main theorem of the article that gives optimal indices in the sense that cannot be improved the indices. Assume G non-abelian because the abelian case is simpler. And let me define this strange index. Here, the maximum is taken over every closest subgroup H of G, but of dimension strictly less than M. Remember, M is the dimension of G, right? And here is the optimal, the first estimates. There are positive constants here, T1, T2, T3, T4. And check here. Used to be in the previous slide, used to be here M. And so we go down up to K max, this strange index. Okay? Yes, index. We go down up to K max. And here we were able, remember, there used to be a 1 here. In the sample estimate, we put new 1 here. And we go down only until 2. So it seems we haven't effort enough, right? But we also prove why is the word optimal in this title is because check here, for instance. What about if you put in place of K max the previous one, K max minus 1? Well, what is showing this is this over this, I mean this over this with K max minus 1. This is not bounded by above. So this index is really the optimal one. We cannot go, we cannot put a lower index there, right? This is optimal. And the same with this, right? The same with this, with the lambda 1, the first eigenvalue. And here we have 2, but here we have 4, which means that, well, you cannot put 4 there, but it might be possible to put 3 or 2. 2 is already known, but I was not able to prove whether we can or not put 3. But when G is semi-simple, know that 2 is the optimal index, right? You cannot put 3 because this, right? Diameter over mu3 is not bounded by above by a positive number because the infimum among all the left-invariant metric is 0, right? So it is optimal in the semi-simple case, this theorem. It gives that all these indexes are optimal when G is semi-simple, which is a case that I am more interested. Right? I claim that this is also possible in the general case, but I was not able to prove. Okay. So the conclusion of this, I mean, these are independent estimates, right? We estimate lambda 1 on the one hand and on the one side and diameter on the other side. And I copy and paste the same as before. And if we multiply this time the square of this, which is the functional that we want to bound by above, and the one that Peter Lee bounded by below, we obtain this. And the problem is that when K max is strictly larger than 2, this is not bounded. This is not bounded. That's a point. Okay, and the same here. It's not bounded by below by a positive number. Okay, so the conclusion is that these extremes are not enough unless K max is equal to 2. When K max is equal to 2, that's great because they cancel and we have a bound. But K max is equal to 2 exactly in this case. Okay, so in some sense, the strategy used in SU2 and SO3, the strategy of bound these terms independently and then put together, holds only for them and not any other compact degree. Okay. Okay, and now let me end this first lecture with a partial answer to the conjecture. Okay, so now remember a few slides ago we fixed a positive definite symmetric map and we pick the decomposition in eigenspaces. Now we fix the decomposition at the beginning, okay, in one-dimensional subspaces. And let me denote by K the index, the smallest index, such that the first K here are bracket generating. This subspace is bracket generating. What means bracket generating is this subspace generates as a Lie algebra, the whole Lie algebra. Okay, in some sense, the smallest Lie algebra containing this subspace is G. There is no any proper subalgebra containing. That's a notion of bracket generating. Okay. So the theorem said that you fix this and you pick K, the smallest index. This is unique, of course. And the theorem says that there is a positive constant, but it depends on the decomposition. That's the problem. And this is true. We have the upper bound, but for some subclass of left-invariant metrics, we explain now. Only the left-invariant metric associated to positive definite symmetric endomorphisms that satisfy this. Okay, this is something not easy to read. In some sense, this is P, and this is Q, right? And this is AK. P is the sum between A1 and AK minus 1, but I think graphically it's simpler to see here, right? This is the index K, okay? And this is P and this is Q, the same here. And the idea is 5 is of the following form. It has an eigenvalue here, mu, any mu. And here we put in this block K minus 1 times K minus 1, anything, of course, positively definite symmetric map, right? And while not anything, the eigenvalues there cannot be larger than mu. Cannot be larger than mu. Okay? And the same here. So in some sense, if we put something in this block, it means that phi preserves left-invariant P and Q. This is in other words we say, right? So for this particular subset of metrics, it holds this upper bound. For instance, when K is 2, you can find two vectors in a semi-simple algebra. When G is semi-simple, you can find two vectors such that they are bracket generating. Okay, it is possible. It is probably not intuitive, at least it was for me, but this is possible. So for G semi-simple, you can find the composition such that A1 and A2 are already bracket generating. And the dimension I want to compare the dimension of this subset with the dimension of the space of all left-invariant matrices. And the dimension is this, right? Now that it is not the same, of course, because it's a proper subset, but it's not so far. I mean, the order is m squared over 2, the same as the row here, right? Okay, here it ends the first part of the lecture. In the second one, I invite you to watch it, and we will give the ideas of the proof of the optimal indices, right? Of course, it's going to be a bit technical. It's the idea of the proof, and maybe you prefer to go to watch any of the other fabulous videos. But let me try to convince you. The idea, it involves sub-Riemannian and singular Riemannian left-invariant structures of G. Okay, singular in the sense not a singular that has a point with a corner or something like this. Is something else that I will explain in the next video, and we will give some precise reference, not only articles and recorded talks. Okay, thank you very much. See you in the next talk, maybe.